This training module will introduce you to the basic principles of pressure. Pressure or differential pressure measurement in a process or plant can be used as direct measurement to detect the pressure in a pipe, or for example the differential pressure between input and output of a filter, but also in a lot of applications for the measurement of some other variables. These are flow rate in a pipe, level of fluid in a tank, density of fluid or interface level of two fluids in a tank. Flow rate is measured with a primary element and a differential pressure transmitter. For the fluid level in a tank, you also need a differential pressure transmitter if the tank is pressurized. If the tank has a connection to the atmosphere, this means it is not pressurized, you can use a gauge pressure transmitter. For density of fluid and interface level, a differential pressure transmitter is always necessary, very often combined with diaphragm seals. Pressure as a process value is measured to protect plant accessories and machines, and to guarantee a good quality of the product for which the process is utilized. Examples are measurement of gauge pressure of feed water, steam and boiler pressure to protect the plant and of course people, and to ensure the requested volume of the product in a power plant. Absolute pressure measurement at different levels of a column to achieve the right product and product quality in a refinery. Gauge pressure measurement at a compressor to protect the machine against cavitation pitting. Measurement of differential pressure between input and output of filters to recognize when the cleaning process has to be started. A common application of a differential pressure transmitter is for sensing flow rate by use of a primary element like an orifice, a nozzle, a venturi or similar, and a differential pressure transmitter. The advantages of this kind of measurement compared with alternative methods of flow measurement are: it is a cost-saving solution even for big pipe diameters, especially when using an orifice or pitot tube as a primary element. It can be used even if the process temperature is high, for example for steam flow measurement. The primary flow element, in the picture is shown a so-called wedge meter, has an internal restriction to reduce the cross-sectional area of the pipe. This restriction causes fluid velocity to increase as it passes by the restriction. According to Bernoulli's energy equation, the increase in kinetic energy is balanced by a corresponding decrease in potential energy, static pressure. Taps placed on either side of the restriction see a differential in static pressure, produced as a result of this decrease in potential energy of the fluid. The differential pressure measured by means of an obstruction in the stream is not linear with flow. To make the signal linear with flow, it is necessary to perform an arithmetic conversion by extracting the square root of the pressure differential signal. Electronic differential pressure transmitters are available with square root extraction electronics built into the instrument as standard. Standard differential pressure transmitters can be used for this application, as long as there is no change in density due to changes of process temperature and or process pressure. As soon as the density is different from that which was used to calculate the data for the primary element, the measurement errors increase. In this case, a multivariable transmitter should be used, which measures differential pressure, process pressure and temperature, calculates the current density of the fluid, and then the mass flow. Liquid level measurements can be made using a differential pressure type transmitter or gauge pressure type transmitter. Typically, this is determined based upon whether the tank is open to the atmosphere or whether it is closed. The liquid produces a hydrostatic pressure depending on its density, which is linear to the current level and is measured by the connected transmitter. Open tank liquid level measurement means that the tank is open to the atmosphere. Any change in atmospheric pressure affects the process fluid pressure within the tank. In this type of level measurement application, the low side of the transmitter measures atmospheric pressure, thus cancelling out the effects of atmospheric pressure on the tank fluid level. The high side of the transmitter is connected to the tank, and thus measures the actual level of fluid in the tank. To calculate the range to which the transmitter should be adjusted to, you must know two distances. One is the distance between the lower tap and the assigned minimum level of the tank, where the transmitter output signal should be 0%. It is called H1 in the drawing in front of you. The other one is the distance H2. It is the distance between the minimum level and the assigned maximum level, where the transmitter output signal is supposed to be 100%. In addition to the distances, the specific gravity of the process liquid must be known. The P-range calculation is the following. Lower range value, LRV, equals height, H1, multiplied by specific gravity of process liquid, SG. Upper range value, URV, equals lower range value plus height, H2, multiplied by specific gravity of process liquid, SG. Liquid level measurement in a closed tank. A closed tank application is where the tank or vessel is pressurized due to process requirements. Piping the low side of a differential pressure transmitter to the top of the tank, the measured value is the pressure difference between top and bottom. Connection between transmitter and tank can be done either with impulse pipes or with diaphragm seals. To avoid problems with impulse pipes, like condensate in the low pressure side, the use of diaphragm seals is very common. When approaching level measurements with a pressure or a differential pressure transmitter equipped with diaphragm seals, particular attention has to be given to the capillary's fill fluid. The fill fluid will have to be compatible with both operating process and ambient temperature. In case the tank will be depressurized and working in a vacuum, it is suggested that the transmitter is installed below the lower tap. To calculate the range to which the transmitter with diaphragm seals should be adjusted, different values must be known. One is the distance H1 between the lower tap, where the high pressure side of the transmitter is connected, to the assigned minimum level of the tank, where the transmitter output signal should be 0%. The next one is the distance H2 between the minimum level and the assigned maximum level, where the transmitter output signal is supposed to be 100%. For consideration of the filling liquid in the capillaries, the distance H3 between the lower and the upper tap must be known, and of course the specific gravity of the diaphragm seals filling liquid. In addition to the distances, the specific gravity of the process liquid must be known. The DP range calculation is the following. Lower range value, LRV, equals height, H1, multiplied by specific gravity of process liquid, SG, minus height, H3, multiplied by specific gravity of liquid in capillary, SGC. Upper range value, URV, equals lower range value plus height, H2, multiplied by specific gravity of process liquid, SG. The preceding method leads to density measurement in a tank. In this case, a homogeneous liquid of changing density in the tank will exert varying pressure on the transmitter depending on the change in density. This measure can be applied either in open or closed tanks, and with clean or dirty fluids. As long as the level remains above the top tap, and as long as H is constant, the transmitter will respond to changes in density. Density is weight per unit volume. For example, kilograms per cubic meters or pounds per cubic feet. If the density increases, the pressure on the lower tap increases, and so does the transmitter output. Typically, as in level measurement, a differential pressure transmitter is used, because the difference between top tap and bottom tap has to be measured. To calculate the range to which the transmitter should be adjusted, the distance between the lower and the upper tap, called H1 in the drawing, must be known. Because the measurement is performed by a transmitter with diaphragm seals, the specific gravity of the filling liquid in the capillaries must be taken into consideration, in addition to the fluid in the tank. Therefore, the specific gravity of the diaphragm seals filling liquid must be known, and of course, the specific gravity of the process liquid. The dP range calculation is the following. Lower range value, LRV, equals height, H1, multiplied by minimal specific gravity of process liquid, SGPL, minus specific gravity of liquid in capillary, SGC. Upper range value equals lower range value plus height H1 multiplied by maximal specific gravity of process liquid, SGPH, minus minimal specific gravity of process liquid, SGPL. Interface level measurement is measuring the position of an interface between two separated liquids, such as oil and water. It can be applied either in open or closed tanks, or with clean or dirty fluids. It is measured using a differential pressure transmitter. Liquids 1 and 2 are of different densities, and as long as the total level in the tank is above the top tap, and as long as the distance h remains constant, the change in density, and hence the hydrostatic pressure, will change with interface level change. Very important notice. Total liquid level must always be above the top transmitter tap. Both the densities must be predetermined and should remain constant for accurate measurement. To calculate the range to which the transmitter should be adjusted, the distance between the lower and the upper tap, called H1 in the drawing, must be known. Because the measurement is performed by a transmitter with diaphragm seals, the specific gravity of the filling liquid in the capillaries must be taken into consideration, in addition to the fluid in the tank. Therefore, the specific gravity of the diaphragm seals filling liquid must be known. In this case, the interface position is to be measured. Therefore, for the range calculation, you must know the specific gravity of both of the liquids in the tank. The dP range calculation is the following. Lower range value, LRV, equals height, H1, multiplied by lower specific gravity, SG1, minus specific gravity of liquid in capillary, SGC. Upper range value, URV, equals lower range value plus height, H1, multiplied by higher specific gravity, SG2, minus specific gravity of liquid in capillary, SGC. Okay, you've seen a lot of facts and information, and I'm sure a lot of it is not new to you. What have you learned so far? What the physics of pressure is. Why it is necessary to measure pressure. What the deriving non-pressure variables are and how they can be measured. So far, so good? Please click on No to repeat the chapter, or Yes to continue.